Hello all, welcome to Masterspharma. We are going to discussing about chair conformation of cyclohexane. Okay, in this chair conformation is excellent explanation about the stability of cyclohexanes. Generally, we know carbon containing generally 4 bonds, 4 sigma bonds, and the shape is tetrahedral shape. And the bond angle is 109 degrees 28 minutes. This is very basic information. The shape or geometry is tetrahedral. So this is very stablest form. Carbon containing tetrahedral angle and 109 degrees 28 minutes is very stablest conformation. But we know this is the general structure of cyclohexane in every textbook. This is the representation only. So if we can isolate one carbon atom here, so the bond angle is 120 degrees. 120 degrees. So according to mathematical, this is 120 is correct. But according to chemistry, the stability of carbon, this is not at all correct structure. Okay. So before SM theory or Sachet-Moore theory, there is a theory that is called Bayer-Strain theory. So according to Bayer-Strain theory, cyclopentane is more stable remaining compared to cyclobutane and cyclopropane. So Bayer explained about these 3 structures. These 3 structures. This is cyclopropane 3-membered ring. This is cyclobutane 4-membered ring. Here cyclopentane 5-membered ring. So this is very stable conformation. This is stable conformation. Stable one. So maybe direct question from this area, right? So this area, which of the following is very stable conformation according to Bayer-Strain theory? Answer is cyclopentane is the very stable conformation, right? So Bayer is unable to explain the cyclohexane stability because according to Bayer-Strain theory, there is a formula. So the formula is not obeyed by this structure. That's why he could not explain. He failed. That is the drawback of Bayer-Strain theory. So to overcome that drawback, we have SM theory, right? In that SM theory, there is a famous stable structure that is chair conformation. Chair conformation. Okay. In this chair conformation, Sachet-Moore theory. So in this Sachet-Moore theory, Sachet-Moore explained the stability of cyclohexane, that is especially chair conformation. We are going to concentrate on chair conformation. Okay, here this is the structure is look like chair, that's why it is called chair conformation. Okay, so we know, we are very familiar with this structure, that's why just better understanding I am going to write the structure here. So better to write the structure here. So this is called cyclohexane 1, 2, here 3, 4 and 5, 6. Okay, cyclohexane. Same, give the numbering 1, 2, here 3, 4, 5, 6. So the structure is similar to chair, that's why it is called chair conformation. Okay, numbering is clear, right? Can I rub the numbering? Yes, okay, fine. So just remind, these are the positions 1, 2, 3, 4, 5, 6. Okay. There are 2 types of hydrogens here. So here the formula is C6H12. Automatically here also C6H12. This is the molecular formula. 6 carbon atoms and 12 hydrogen atoms. Right? Here there are 2 types. One is axial and the other one is equatorial. One is axial and the other one is equal type of hydrogens here. Axial hydrogens and equatorial hydrogens. Coming to the axial here. So here number 1. So we can simply travel from adjacent atoms. That is better understanding. Okay, we can easily find out the type of hydrogen here. Okay, right. So here one is in between. This one is in between 2 and 6. Coming to the 2. Here 2. and 6. So you can start traveling from adjacent carbon atom. So 2 to 1, the traveling route is upside, okay? The traveling route is upside. And 6 to 1 also traveling route is upside. We are going to reach the first position. That's why we can start traveling from the adjacent carbons, okay? So here 2 and 6. So upside, we can draw one upside line. Okay, same. We are going to reach at second position. So traveling from 1 and here 3. Here 1 and 3 we are going to travel. Okay, right. So 3 to 2 downside and 1 to 2 also downside. Both are downsides. So we can draw one downside line. Then coming to third in between 2 and 4. Okay, so here 2 to 3 upside route and 4 to 3 also upside route. So we can draw one upside line. And coming to the fourth one, 4 in between 3 and 5. So 3 to 4 downside and 5 to 4 downside and 3 to 4 also downside. So here we can draw one downside line. Coming to the fifth, 4 and 6 upside and upside, here also upside. Coming to the sixth one, here 1 and 5 both are downside. So along with the line, that is called axial. Okay, along with the line is called axial. That's why all these 6 hydrogens are called axial hydrogens. Representation is HA. Here axial hydrogen. Third position also upside axial hydrogen. Fourth position axial hydrogen. The representation is HA. Here also axial hydrogen. And sixth one also axial hydrogen. So axial hydrogens are finished. At first position axial hydrogen is upside and second position it is downside. Coming to third one upside, fourth one is downside, fifth one is upside and sixth one is downside. So this is axial hydrogen representation. Then coming to the equatorial. If it is one is automatically upside, another one is downside. So in first case or first position, here this is a upside and automatically another one is downside. Okay, coming to second position, already downside, so we can draw it upside. Coming to third one, already upside, so we can draw a line downside. Here already downside, then go to upside. Here already upside, so we can write downside. Here already downside, so we can write upside. Okay, so this is called equatorial. Representation is He, not helium here, hydrogen, equatorial position. Equatorial, here also hydrogen, equatorial position. Coming to the third one downside, equatorial. Fourth one also equatorial. Fifth also equatorial. And sixth here, this is equatorial. Okay, clear? 6 axial. So axial is 6 and equatorial also 6 hydrogen atoms. Okay, axial, equatorial, clear. Then coming to the above the plane and below the plane. This is very important topic. Okay, don't confuse about above the plane and below the plane, axial and equatorial positions. Right, axial, equatorial, clear. Then we can go to upside or downside. Okay, right. Yeah. So again, I am going to write the chair conformation here. This is chair conformation. Here we know this is upside. Second one is downside. Third one is upside. Fourth one is down and up. Here downside. So 3 hydrogens. Those are axial hydrogens upside. Clear the statement? Next, 3 hydrogens, those are equatorial hydrogens, also upside. Then, what about equatorial? Here downside, here upside. Coming to here downside, here upside, here downside, here upside. So, 3 hydrogens equatorial. Yeah. Sorry, here axial, not downside here. Here downside. Yeah. So first case we are discussing about only hydrogen axial, right? 3 axials. These 3 axial positions are 1. Next, 3, next 5. So first position axial, third position axial and fifth position axial at upside. Okay, next coming to the another set of axial hydrogens. So here the numbering is 2, 4 and 6. So 2, 4, 6 hydrogens downside. Once again check here 1, 2, here 3, 4, here 5 and 6. So first position upside, third position also upside and fifth position also upside. These three are upside axials. Okay. Next, these three are downside axials. Okay. Next, equatorial. 3 hydrogens equatorial below the plane and above the plane, or upside or downside. So at first position this is downside. Okay. So best representation I am going to write the structure is like a square box. Okay. Equatorial downside, and here also next second position, here third position equatorial also downside. Next fifth position equatorial downside. Clear? Next. So 3 hydrogens equatorial downside. Next 3 hydrogens equatorial upside. So how can we give the numbering? 3 equatorial hydrogens, 1, 3 and 5. 1, 3, 5. Automatically upside equatorial hydrogens are 2, 4 and 6. Don't confuse. Okay, there are 2 types of hydrogens only. 6 are axial and remaining 6 are equatorial. But in those 12 we can divide into 4 parts. 3 set, 3 set, 3 set and 3 set. So above the plane 3 axial and 3 equatorial. Below the plane 3 axial and 3 equatorial. Better to write this formula. 3 axial, 3 equatorial above the plane. Above the plane. So same. Next to 3 axial, 3 equatorial below the plane. So total 12, right? Here 6. So 6 are above the plane, 6 are below the plane. In that 6, half of axial, another half is equatorial. Here also, below the plane combination, half of the axial and half of the equatorial combination. This is the chair conformation. Okay, fine. Then coming to extract one hydrogen atom at any area. Okay, if you can choose randomly one hydrogen atom. For example, we can isolate carbon number 3. So how can we finalize? The carbon is having 109 degrees, 28 minutes and a tetrahedral shape, and whatever the requirements to stabilize a carbon atom is fine. Yeah, see. So this is the chair conformation. Yeah, chair conformation. We are going to highlight here this third position. So this third position, upside one bond and completely downside one. Here horizontal, here light horizontal. Okay, this is the tetrahedral shape. Okay, shape okay, tetrahedral, not hydral, hedral, HEDRAL, tetrahedral. Bond angle is 109 degrees, 28 minutes. So that's why it is very much stable. It satisfies all the rules and stability rules of the carbon atom. That's why this representation is very famous for stability of cyclohexane. In the cyclohexane or cycloalkanes, chair conformation is very much stable conformation. Okay, this is explained by Sachet-Moore. That's why it is called Sachet-Moore theory. So how can we convert? How can we convert the structures or the functional groups or the substituents on chair conformation? We will see in next class. Okay, thank you all of you.